We're going to work through how interference plays out in several different cases, and fairly common cases where interference occurs. First off, now if a wave is reflected, there can be a change of phase. Change of phase. Now generally, waves, when you come to a boundary between two media, you get the wave coming in, and some of the light gets reflected, some of it gets refracted. So if the index of refraction of region 1 is greater than region 2, then there is no phase change in the reflected wave. However, if the index of refraction is less than, index of refraction region 2 is less than region 1, there is a 180 degree phase change. Okay, so a wave bouncing off, if N2 is less than N1, a wave bouncing off here will undergo a 180 degree change of phase. Okay, meaning that if a light wave was to come straight in and bounce back, then it was to change phase by 180 degrees, well then there would be destructive interference, because if it's 180 degrees out of phase, that means it's half a wavelength out of phase. So, and now we're going to show how this plays out in several different scenarios involving reflection. Now, as is always the case, if there's a multiple of the wavelength difference in path length, constructive interference will occur, and if there's an odd half multiple of the wavelength path length difference, destructive interference will occur. Now, the first case we're going to discuss here is what's called an air wedge. And what an air wedge is if you have one plate of glass lying flat, and then a second plate of glass is propped up at a little angle here. Okay, and there's something, whatever is here is holding this up, but this glass is propped up at some angle. Okay, now, this drawing is dramatizing this. The book does an example where this thing holding up the one end of the glass is a hair. I've made this bigger for the sake of seeing what's going on, but this doesn't have to be this at this much of an angle. It could be, that you can't even see a difference between this air wedge versus two plates just resting flat on each other. So be aware of that. Now, so what happens here? So what happens here is that you have light that's incident on here, and some of it is reflected off this bottom surface of the glass. Now, glass has a higher index of refraction than the air. So this is our air wedge, air in here. Glass has a higher index of refraction than air, so there is no phase change in the stuff reflected off here. But some of it is transmitted and then gets reflected off the upper surface of this lower glass, and then it comes back and does its thing. All right, and it refracts here. I didn't draw that very well, but whatever. In this case, however, at this interchange right here, there is a 180 degree phase change, whereas here there is no phase change. So then the path length difference between these two rays has a couple pieces. So this ray goes down a distance, some distance, which we call d, and it reflects back up close enough that this distance is still basically d. So there's a path length difference, which I'll call delta L, of 2 times the distance, but this is also reflecting 180 degrees out of phase, which essentially is the same thing as a path length difference of half a wavelength. It's just as though it's traveled a half a wavelength further. So our effective path length difference is 2d plus half times the wavelength. Okay. So in the case of the air wedge, we get constructive interference, where 2d plus half a wavelength is equal to m lambda. So we divide through by lambda, we get a 2d over lambda plus a half equals m. And in this case, m is 1, 2, 3, etc. Okay. Similarly, for destructive interference, we get destructive interference when that 2d plus lambda over 2 is equal to an m plus a half lambda. Okay, and again, so dividing by wavelength gives us a 2d over lambda plus a half equals m plus a half. So that gives us that a 2d over lambda equals m, and that is the condition for destructive interference. And for destructive, in this case, m starts at 0, whereas it started at 1 for constructive interference. Now, this distance between the plates increases linearly as we go this way, which means that the light and dark fringes that you see are evenly spaced. When you shine a light with a given wavelength, when you shine a light with a given wavelength, you get evenly spaced light and dark fringes because this distance increases linearly and m goes up 0, 1, 2, so that's also a linear relationship for m, arithmetic relationship, which corresponds to a linear relationship. And so we do get evenly spaced fringes out of our air wedge. Okay. Another example of where this reflection causes an interference pattern are what's called Newton's rings. This is kind of neat. In Newton's rings, you have a flat piece of glass, and then you have a curved piece of glass on top of it. Okay, so this is in 2D, of course. This might be like a bowl made of glass or something. Now, the principle for Newton's rings is essentially the same as for the air wedge. It's just in Newton's rings, now our distance doesn't increase linearly. It increases at some faster than linear rate. So, because this distance changes at a faster rate as you go further and further out, that distance is increasing faster, which means that if you look down from the top, this bowl sort of shape could look like a circle. You get these light and dark fringes, and the dark fringes are concentric circles. However, as you get further and further out, they get more and more closely spaced, because with that distance, okay, I didn't draw that very well. But as you get further out, these rings get more and more closely spaced because that distance is changing at a faster and faster rate as you go along here. All right.